Space travel is humanity's boldest dream. It's a testament to our unyielding desire to reach beyond our limits. But how can a simple equation unlock the secrets of escaping Earth's grip? And what does this equation teach us about the impossible dreams we all carry? This is the story of the Tsiolkovsky Rocket Equation, a formula that doesn't just move rockets but moves humanity forward. Okay, let's break this down. Getting off this planet isn't just about sticking a giant firework to a metal tube and lighting the fuse. It's about math. Yup, math. But before you roll your eyes or start having flashbacks to high school algebra, let me introduce you to the ultimate space cheat code, the Tsiolkovsky Rocket Equation. This little formula has been making dreams of interplanetary travel a reality since 1903. It was cooked up by Konstantin Tsiolkovsky, a Russian scientist who basically decided, I may live in a tiny rural town, but I'm going to figure out how humans can yeet themselves to the stars. He was like the OG space nerd before it was cool. And his equation? It's deceptively simple, yet holds the key to every rocket launch you've ever seen. Here's how it works. Imagine a rocket trying to break free of Earth's gravity, which, by the way, is like running up a down escalator. Except the escalator is 7.8 kilometers per second fast. That's escape velocity, folks. The rocket equation helps engineers figure out how much fuel is needed to hit that speed. Spoiler, it's a lot. The formula ties together a rocket's velocity, its mass, and the speed of the exhaust gases shooting out of its engines. As the fuel burns, the rocket gets lighter, which is where things get fun or terrifying depending on your trust in physics. Tsiolkovsky's genius was realizing that by dumping empty fuel tanks mid-flight, aka staging, you can shed weight and keep the rocket accelerating efficiently. It's like tossing your luggage out the window mid-road trip to get better gas mileage, but in space. But there's a catch: rockets are mostly fuel. Seriously, next time you see one of those massive SpaceX or NASA launches, just know that all that engineering boils down to carrying a giant fuel tank with a tiny payload attached. Why? Because the amount of fuel you need grows exponentially the faster you want to go. It's like trying to save money on avocado toast while dreaming of owning a mansion. Completely unfair but unavoidable. And that's just the beginning. The rocket equation assumes space is a perfect vacuum, which it's not, thanks pesky atmosphere. Launching from Earth means dealing with air resistance, gravity drag, and other real-world buzzkills. Oh, and it doesn't account for the fact that rockets have to survive insane heat, pressure, and, occasionally, exploding. Modern engineers use computational simulations and advanced materials to work around these limitations, but they still bow down to Tsiolkovsky's math as the foundation of it all. Now let's talk propulsion. The secret sauce here is specific impulse, or how efficiently a rocket turns fuel into thrust. It's kind of like miles per gallon for rockets. Except instead of miles, we're talking about crossing the vacuum of space. And instead of gallons, it's propellant that sometimes needs to be stored at cryogenic temperatures. No big deal. Chemical rockets, like the ones on the space shuttle, are great for brute force, but burn through fuel faster than your car guzzles gas in traffic. Meanwhile, fancy ion thrusters, think sci-fi spaceships, are slow but super efficient, making them perfect for long-haul trips to places like Mars. Speaking of Mars, here's where Tsiolkovsky's equation gets really cool. Every single step of a mission, like NASA's Perseverance rover or SpaceX's plans for colonizing Mars, depends on crunching the numbers in this formula. Engineers calculate the dV, that's delta V, or the velocity change, for everything, leaving Earth, landing on another planet, and coming back. Want to know why staging is so important? Because without it, missions like Apollo 11 would have needed a rocket the size of Mount Everest to carry enough fuel. And while rockets have limitations, modern tech is bending the rules. SpaceX's reusable rockets are revolutionizing the game, cutting costs and challenging old-school rocket design. At its core, Tsiolkovsky's rocket equation isn't just math. It's a love letter to humanity's obsession with exploration. Every rocket launch, satellite deployment, and distant probe is a nod to his brilliance. And as we dream bigger, whether it's space elevators, nuclear propulsion, or making Mars our second home, this equation remains the foundation for turning those dreams into reality. I'll leave you to discuss in the comments. What's your favorite futuristic propulsion idea, and how soon do you think we'll need it? Don't forget to subscribe if you haven't already. Take care of yourselves, take care of your loved ones, and I'll catch you soon in another video.